Today we're going to talk about once you have conducted your experiment and you have used the collected data to plot the graph, how do you analyze the graph? What are the main different information you can get from the graph? Now let's take a look. The first graph is showing here is a basic experiment. When time goes by, you will have less amount of reactant in your system and more product in your system. As you can see, the rate of reactions of both graphs are slowly decreasing over time, meaning that the slope of the tangent that you are drawing at different time points is less steep when time goes by. So for my product graph, which is this red graph over here, if I were to draw two tangents over here, first one at the first time spot and second one at the second time spot as well, the slope of the first one is so much steeper than the slope of the second one, meaning that the rate of reaction is being slower and slower. Same thing happening with my reactant. So if I were to draw two tangents at the earlier time slot and another tangent at the later time slot, the slope of the first one is so much higher than the slope of the second one as well, meaning the rate of reactions is decreasing as well. Why is that? Well, the reason for that is, as we have talked about in the last class, is because the amount of reactant in your system are slowly decreasing over time, meaning that the concentration of your reactant is decreasing. So concentration of your reactant is decreasing. We all know that concentration contributes to the rate of reaction. So when the concentration is slowly decreasing, you're bound to have less reaction or less rate of reaction as well. That's why throughout the experiment, the reaction is going slower and slower over time. I'm sure a lot of you have seen this graph before. This is a graph that compares two experiments that are of the same kind. Let's assume the blue graph is experiment number 2 and the red graph is experiment number 1. As you can see, the initial rate of both reaction is different, and at the final point, the reaction graph has reached to the same point. Reaction number 1 has a higher initial rate because of the slope of the initial rate tangent is higher than the slope of the initial rate tangent of the reaction number 2. And both graphs eventually reach at the same point. That means is that finally the volume of carbon dioxide that being produced by reaction 1 and reaction 2 is actually the same. So a lot of things can contribute to this kind of graph. If you have the same temperature or you have the same concentration and also the initial amount of reactant is the same, will contribute the same amount of the product in the end as well. So temperature, concentration, if you have add some catalyst, that will contribute to this kind of graph as well, which is a fairly simple graph. Now let's take a look at the second graph. This graph means that you will have a different initial rate and you will produce different final products. So different initial rate and different final product for both of the graphs as well. What usually contributes to this type of graph is a change in the concentration and the amount of reactant. So for example, if I have an excessive amount of magnesium for both of the reactions, and I will name this reaction number 1, this one reaction number 2. So for reaction number 1, I have 50 centimeter cubes of 1 moles per liter hydrochloric acid, and for reaction number 2, I have 500 cubic centimeter and let's say 5 moles per liter hydrochloric acid. As you can see that for both of these reactions, I have different concentration and also the final moles of my hydrochloric acid, which is my reactant, will be different. So reaction number 1 will have a less concentrated hydrochloric acid as well as less amount of hydrochloric acid. A quick instruction on how to calculate the amount or the moles of hydrochloric acid. You simply need to use this equation. Moles equals concentration times volume, 1 moles per liter times 50 cubic centimeter 50 cubic centimeter is actually 50 milliliter, and that is 0.05 liter. If you time those two together, it will give you 0.05 mole. Okay, that's for the reaction number 2. For reaction number 1, you're gonna do the same thing. Initially, I have 500 cubic centimeter as well as 5 moles per liter. N equals C times V. I have 5 moles per liter times 500 cubic centimeter. Make sure to change this into milliliter. And in the end, milliliter and liter transfer. If I change milliliter into liter unit, this whole thing, 500 milliliter, will be 0.5 liter. Then I will have 5 moles per liter times 0.5 liter. That will be 2.5 moles. So initially, I'll have 2.5 moles of hydrochloric acid for the reaction number 2, and only 0.05 moles of hydrochloric acid for reaction number 1. That means for both of the concentration and the amount of hydrochloric acid, reaction number 2 wins. So we will have a higher initial rate and also a bigger product. Sometimes you might see a graph like this. The graph is plotted with the concentration changes of both reactant and product. So C is usually the rate of a product, and A and B are usually represented by the rate of the reactant. Okay, so A and B usually are two different experiments, so we can take a look. With the decreasing time, with the decreasing amount of reactant, for both A and B, you need to do the same thing. For A, you need to take a look at the initial slope of your rate of reaction. For B, you need to look at the initial slope of your rate of reaction, so the initial rate of your reaction by drawing a tangent and figuring out the slope. And also, you need to look at what is the loss of the reactant of A and what is the loss of reactant in terms of B. So that gives you an idea of what is the amount of product being produced in the end. If you have less amount of A being consumed, less amount of reactant being consumed in A reaction, and more amount of reactant being consumed in B reaction, that means in B, you will definitely have more product as well. Okay, now let's take a look at one quick example. So the red curve on the graph shows the volume of oxygen formed during the catalyst decomposition of 50 cubic centimeter of 1 mole per liter solution of hydrogen peroxide. Which change will produce the blue curve? Check all that applies. So I have several different ones. I have increasing the temperature or decrease the temperature. Use 100 cubic centimeter of 0.5 moles per liter solution instead, or use 50 centimeter cubes of 0.5 moles per liter solution instead. So pause the video for a second. Okay, so now you can take a look at the rate of reaction. It's apparent that both of the reactions will reach the same point. That means you will have the same amount of reactant. Red one will have a higher rate of reaction, so higher. Blue one will have a lower rate of reaction. So if you take a look, decreasing the temperature, you will produce a blue curve. For the next one is, if you take a look at the initial amount of the concentration of your reaction and the volume of the concentration of your reaction. If you have used a kind of solution that has been able to decrease the concentration, but also are be able to produce the same amount of final product, meaning your initial amount of your reactant is the same, that means that's a good choice as well. So both decrease the temperature and also lowering amount, but also increasing the total volume. That gives my initial solution a 0.5 times, this one changed to 0.1 dm minus 3, 0.0 times 0.1 equals 0.05 moles of my solution. The second one gives me 0.5 moles per dm3 times 0.05 dm3, and that gives me a less amount of solution than 0.5. So for this one, I will use 1 times 0.05. That will give me 0.05 moles. So both C and the initial amount is the same, and also C applies to a decreasing amount of temperature concentration. As you know that you are not allowed to use calculator in IB multiple choice, so instead of using all this calculation to figure out the initial amount, there's some route that you can use when you're doing the multiple choice calculation. Let's say initially we have the same amount of volume and same concentration over here, but also you want to take a look at the changes in concentration. The concentration has been halved compared to the first one because 0.5 is 1 divided by 2. And the volume has been doubled the amount. If I time these two, the total amount, 2 times 1/2, is actually doesn't change at all. So C is also a good choice, and you don't have to do the heavy-duty calculation at all. I have a second example over here. Curve X on the graph shows the volume of oxygen formed during the catalytic decomposition of a 1 mole per liter solution of hydrogen peroxide. Which change will produce the curve Y? So curve X is 1 mole per liter. I have several different options. I can lower the temperature, adding more water, use a different catalyst, or adding some 0.1 moles per liter hydrogen peroxide solution. Pause the video for a second. Okay, so once we take a look at reaction number X, or first reaction X, which one will produce the same curve as Y? As you can see that the total amount of product is getting bigger from X to Y. And also the rate of reactions, the curve itself is decreased. So the rate of reaction, or the slope, the curve is from X to Y is decreasing as well. So you need to look at something that produces a bigger amount of product and something that decreases the rate of reaction as well. By lowering the temperature, only contributes to decreasing rate of reaction, but does not change the total amount of product. Adding water will change the rate of reaction, but same thing with lowering the temperature, does not change the total amount of product. Use a different catalyst is the same kind of idea. By adding some 0.1 moles per liter hydrogen peroxide solution, if you are adding 1 moles per liter by 0.1 moles per liter, you're actually adding a solution that's so much less concentrated in your original solution. So in another way, you are diluting your solution, but you're also adding a small amount of your reactant as well. Therefore, your rate of reaction will change while getting slower because you are diluting it, you are lowering the concentration from 1 going down, and in the end, you will have a bigger amount of product being produced because you are adding your initial reactant as well. That's why you will have a larger amount of your final product as well. Excessive magnesium will add to the beaker of aqueous hydrochloric acid. A graph of the mass of the beaker and content was plotted against line 1. What change in the experiment could give to line 2? Either using a more accurate instrument to measure time, or the same volume of more concentrated solution of hydrochloric acid, the same mass of a magnesium in smaller pieces, or a lower temperature. Okay, pause the video for a second.